for an introduction. Let me, before I even explain to you why we need privacy-preserving machine learning, let me acknowledge my collaborators. I have two brilliant friends working with me on this topic. This is Roman Vashinin from UC Irvine and Marj Boidihajo from UC Irvine. Marj is actually got his PhD from Texas A&M a few years ago. Well, he got it when he was 17, much earlier than most people. A really smart guy, and we have a lot of fun working on this topic together. Now, why is the need for privacy-preserving machine learning in the first place? Let me give you a few examples. For example, you might have an Android-based phone. Then you should know that Android by Google was really developed to get access to your private information. That was the real purpose. And why do we know that? Well, here are a few examples. Google is tracking you on your Android phone all the time. You could say, why I don't like that, I turn off my phone. Well, Google is still tracking you. You could say, well, I'm using all the apps. You know, Google is still tracking you. You can even take out the SIM card of your Android phone, and Google is still able to track you on your phone because the phone is designed in that way that it's built into the chip, so you cannot opt out of this tracking. So it's really not about your choices. Google wants to control you in that sense. There are a lot of other ways how Google gets access to information, but Google is, of course, not the only culprit here. Facebook is a serial privacy violator. You know, of course, the Cambridge Analytica scandal. Well, that's just one of the things, but there are many other situations where Facebook tries to get access to information without your consent. For example, whenever you download an app, most apps, about 80% of the apps, immediately share all the information on your cell phone with Facebook. It doesn't matter if you have a Facebook account or not. You don't have to have a Facebook account. These apps are essentially designed to really get information from your phone. For example, the Weather Channel app, if you have that on the phone, then it accesses all your contact addresses, all your videos, all your pictures, and sends them to Facebook. Has nothing to do with the Weather Channel, right? But that's what this app does. When Europe introduced these new privacy laws, before Europe introduced these privacy laws, Facebook had all their non-US users registered in Ireland under Irish law. Once this new law in Europe started, Facebook said, oh, we want to follow the European law in spirit. But secretly, they moved all the users that are not registered in the US to the US because the US law is much, much more lenient. So they say the one thing, but they do the other thing. So there are many, many other examples where Facebook really tries to get access to information, and usually in a way where they try to hide it from you and do it in a way to, you know, really exploit your privacy. But again, they're not the only example. Hertz, Verizon, many, many other companies to follow in the same pattern. And these companies, of course, complain that these, well, that our concerns are not really warranted, and they really care about our privacy. But they don't really care enough about them. For example, Zuckerberg voted down a proposal from shareholders to get more transparency, to get more insight into what is going on at Facebook regarding privacy. And Google did the same thing. And one another example, a sad example, I think, when Benedict Evans tweeted that you should really own your data is such a meaningless bullshit slogan, then the chief AI scientist from Facebook, whom many of you might know, happily retweeted this statement. So you really get a clear picture of what Facebook thinks about privacy and the users. All this is part of what is now called surveillance capitalism, which is a new economic system that is built on exploiting and taking advantage of controlling human nature. Sounds dramatic, but there are many, many other examples that would illustrate that this is really going on. And it's brilliantly described in Shoshana Zuboff's book of the same name. And I think it really has disastrous consequences for our society and for our democracy and for our freedom. So privacy is really an important element here, but we cannot just, you know, trust Facebook and Google and these companies with assuming that they will take care of our privacy protection. It's a little bit like trusting Exxon a chevron with, oh, they will take care of the environment. That really wouldn't work very well. So why do we need privacy-preserving machine learning? Well, because machine learning, after all, still does does a lot of good things for us, right? There are many, many examples where machine learning can help a lot. Could it be things like automatic language translation, but much more important, for example, in health. COVID was an example where AI could really have a lot of impact. Cancer treatment, personalized care. There are many, many examples where machine learning, AI, data science are really, really important. But data science needs data. And we are told sharing is caring. But if you really care about your privacy, you need to be careful what you share. So how do we go about this conundrum that on the one hand, we need data to be shared so that machine learning has data to work on, and yet our privacy is preserved? And that brings us to the topic of privacy-preserving machine learning. There are several techniques that are used in privacy-preserving machine learning, or still being developed, I should rather say. Homomorphic encryption, federated learning, on-device learning, anonymization, differential privacy, and synthetic data. There are a few more, but these are kind of the key topics. And in my talk, I will focus on the last three, on anonymization, differential privacy, and synthetic data. As you will see, however, that the path to privacy is really paved with NP hard problems. This is one message of this talk. When I started working on this topic and I wanted to do some real serious mathematics, I quickly learned, oh, this is really, really hard. Okay, so let's start with the first technology of privacy preservation, anonymization. It's maybe the oldest one and still quite often used. It usually goes by the name of k-anonymity, a concept that was developed by Sweeney in around 2000. And roughly you can describe the concept of k-anonymity in the way that you have a databases, like census, for example, and you say that this database satisfies the k-anonymity property if one user, one person in this database cannot be distinguished from k-1 other individuals. So you kind of hide in the crowd. You hide in the crowd of k individuals that are similar. And the mathematical definition is written down here. It's kind of just a translation of what I just said before. And just to give you a quick example, look at the database on the left. Here we have 4 different people with first, last name, age, and race. And they're all different. On the right side, you see how we can turn this into a 2 anonymous database, so k is 2 in this case, by suppressing certain information. So we need to suppress first names or last names or age, or at least make the age less descriptive. And then you see on the right side, each user here appears twice. So this is a k equals 2 anonymous database now. This is a simple concept and it offers some privacy, but it's not really that secure because often you can break this privacy by linking it to other databases. And this linkage attack, as it is called, then often allows you to actually find out the true identity of people. So it's still in use, but it has limited applicability and limited security. This is why then Dwork, a few years later, came up with the concept of differential privacy. Differential privacy is a different take on privacy, and the point here is, well, maybe asking for strict privacy is too much. It's impossible. So maybe we only should ask, well, if you do a medical study, say, then all I can ask from that study is that you would not be able to tell if my personal data were used in this study or not. Okay, so the outcome of whatever data analysis you do should not tell if my personal data were used in the study or not. And this is, so it doesn't really make a difference. And this is the idea of differential privacy. And in this case, I want to go through this mathematical definition. The definition says that the randomized function M gives epsilon differential privacy if you have two databases, D1 and the D2, that differ only by one element, so that these differ really by the absence or presence of one person. And then you look at all outcomes, all measurable sets S that are in the range of this function M. And then you look at the probability. What if I apply my data analysis to the set D1 and I get a certain outcome, and apply my data analysis to the set D2 and I look at a certain outcome, then the probabilities that these outcomes, I want that the probabilities of these outcomes are very similar. That's the point, right? So if I use D1 or D2 and I do my data analysis, the outcome should be very similar. They only differ by e to the epsilon. And so this is the definition of differential privacy. And epsilon, of course, should be small. For example, if epsilon is 0, the smallest choice, then the database is completely differential private. It's independent of which user you throw in or you take out. That's the best case. If epsilon is large, that means, oh, there's a clear difference if one user is present or not, and then I wouldn't have a good privacy protection. So the lower the value of epsilon, the more privacy is guaranteed. How would I then typically make sure that a database or a mechanism is differential private? Well, the standard way is to add noise. For example, Laplacian noise. It doesn't have to be Laplacian noise, but it satisfies certain, it can also be Gaussian noise, for example. But the Laplacian noise satisfies certain properties that are very convenient. And so the typical mechanism to initiate differential privacy is to via this Laplacian mechanism. So that we would add noise, Laplacian noise that scales with 1 over epsilon. Meaning the lower the value of epsilon, the more noisy the data are, and the more privacy we get. The higher the value of epsilon, the less noisy the data are, but the lower the privacy guarantee. And the challenge in practice is how do we choose this epsilon? This is what we call privacy budget. Now, typical values for epsilon, as for example used by Microsoft, Facebook, and other companies, is they strive to use values less than 4. Empirically, this has shown to be reasonably good. And differential privacy is not just a mathematical concept, it's actually used very likely with the release of the census 2020 data. There are some issues with that, we'll talk about the data. But it's really something that companies use in practice. But it also has its problems. This adding noise reduces utility, and therefore people were thinking, what else can we do? And now the concept of synthetic data came up. The idea of synthetic data is you generate data from the original data, you generate artificial data, so they're not the real thing, but they should mimic the real thing in the sense that it duplicates the statistical properties of the original data set, and yet it is not the original data set. So on the one hand, you want to maintain the properties of the original data set. On the other hand, you want to make sure that it doesn't expose sensitive information. This is the idea of synthetic data. Of course, you see there's an intrinsic conflict between privacy and utility. Utility here is, how useful are the data, how accurate are the data, how well do the data represent the real thing. And the intrinsic conflict is, on the one hand, we want the synthetic data to be different. On the other hand, they should be similar to the true thing. And we can, of course, look at two extreme cases here. On the one hand, the synthetic data can just choose them to be the original data. Then have perfect utility. They're as good as the real thing. But of course, there's zero privacy. Or you choose the synthetic data to be just something random. Then you have perfect privacy. There's nothing sensitive revealed. But of course, utility is zero. So you have the two extremes, and really what you want is you want almost perfect utility and you want almost perfect privacy. And we need to see to which extent this is possible. In any case, there's this idea that we should really combine synthetic data with differential privacy, because then you have the best of both worlds. And this is an idea that has been around for a few years, and this is what many companies, startup companies, and also quite a number of researchers in computer science are working on. Mathematicians really have not entered this area yet, but in computer science, this is an important topic. So to illustrate the difference between synthetic data and the classical ways of ensure privacy or trying to ensure privacy, let's look at the images here on the left side. So let's say these are images we want to analyze in some way, but we need to protect the privacy of the people in these images. So k-anonymity or anonymization would correspond to something that I do up here on the right. I try to hide the identity of the people in a very certain way, in a very specific way. So I'm blocking out certain information. I'm somehow suppressing certain information. And what I'm illustrating here is, yeah, but maybe you can still recognize the people. On the other hand, you may lose really important information. If eyeglasses are what you care about, then you lost something really important here. Differential privacy means you add some noise, carefully chosen noise to the data. So what you get is still useful data, but maybe if you had to add a lot of noise, then what you were looking for could be lost in the data. And synthetic data could be illustrated in a way that on the left side, I have the original image, original data. On the right side, I create new faces. You may have seen this deep learning-based generative adversarial networks, yet GAN for short, G-A-N. They are very good in generating faces, new faces, artificial faces out of real faces. So none of the faces on the right are real. These are artificial faces. They do not correspond to real people. A synthetic data set would then be something like this. Now the hope is that the synthetic people here on the right side still have a lot to do with the people on the left side. Now, how do I measure that? How do I quantify that? For example, I could say I want to quantify it by how many people with long hair or bald people do I have on the original data set. I want to have the similar ratio in a synthetic data set. How many people have eyeglasses? How many people have male, female, children, and so on. So I want my synthetic data set to represent the key features of my original data set, and hoping that I actually know what the key features of my original data set are. With faces, it may be easy, but what if these images on the left are images of tumors and I don't really know what I'm looking for in these tumors? How would I know that my synthetic data set reproduces the key features in my original data set when I even don't understand the original data set yet? So there are a lot of issues, of course, that come with synthetic data sets. And how do I know that privacy is really preserved? Maybe in this training process, there's still a footprint left in the synthetic data set that allows me to attack the synthetic data set. And there are examples in the literature, gradient leakage and the other phrases that you may have heard, where you can actually trace back and crack some of the synthetic data sets and find out from which real data sets they came from. So this is not such an easy thing to do. Okay. This brings us back to healthcare. Synthetic data sets are really important in healthcare. And there are many examples where governments really don't protect medical data as much as you think. In 2013, UK planned to sell all the patient data, to companies. Patients could not opt out. So you don't own your medical data. They had to withdraw their plan because there were so many complaints, but this plan may come back. And it's even worse in the US. The Supreme Court in the US ruled in 2011 that companies are allowed to sell your medical data. First, to harvest your medical data and to sell them. You have no right to this data. Well, you have some right, but you cannot prevent them being sold. So your medical data, a very sensible area. Now things get a little bit better, mainly pushed by Europe, and US is way behind, but California is catching up. And this brings us now to this issue. On the other hand, it's good to share medical data, right? It's good to make progress in research. So we understand we need to share data. On the other hand, we want to protect privacy. And this is particularly important in the intensive care unit, ICU, where AI has shown to be really, really helpful in getting insights how to get better ICU treatments. But medical data in the ICU are scarce, and it would be really helpful if you could share ICU data across hospitals. That we can get more people, more data scientists involved in ICU data research. So that's really a bottleneck now, because it's really, really complicated to get access to the ICU data. And because of the scarcity, we really hit the roadblock here. So the ICU is really, for me, the prototypical example where synthetic data would be extremely helpful. But the point is here, high quality synthetic data, not just some, but high quality synthetic data. Because it allows us to protect privacy, and we can really make advances in a very important area of research. There are, of course, many, many challenges with these data. In particular, these ICU data, they are dynamic, they're multimodal, they're heterogeneous. So it's not just one type of data. It's tabular data, electronic health records. You have waveforms, you have time series, you have images, you have spectroscopy data. So you have all kinds of data. And this is the project that got me started on synthetic data. How do I construct heterogeneous, dynamic, multimodal data? Well, it turns out this is really, really complicated, really difficult. And so we started out with a simpler model. Okay, so let's look at the simpler model. Let's look at a really simple model. Let's look at the Boolean cube as a benchmark model. You might laugh and think, the Boolean cube, what's that for a data model? In computer science, this is really indeed a benchmark model for a lot of data analysis. And it does make sense. So what does a data set here look like in this Boolean cube? Well, think of a matrix X. The matrix X is our data set. It has n rows and p columns. The rows of X could be the patients. So again, always think of an electronic health record. So you have n patients. These are the rows. Each patient is a row. And then you have p columns, and these are things you analyze in an electronic health record. It could be, things like gender, occupation, or it could be, does the patient smoke or not smoke? Does the patient have had diabetes, or what's the blood pressure of the patient? All these things can be encoded via zeros and ones, either directly, or you may have to do some one-hot encoding or binary encoding, or you have to approximate it with some binary encoding. But in principle, you can encode all this information on the Boolean cube. So therefore, the Boolean cube became a benchmark model also in synthetic data. So now we have a really simple model, right? So now our life should be much easier. Then how do we measure accuracy of synthetic data? On the Boolean cube, there's a very natural concept. Well, we look at marginals. Marginals would be, for example, one-dimensional marginals would be, well, how many people in your database smoke? How many people, another one-dimensional marginal would be, how many people have diabetes? A two-dimensional marginal would be, how many people smoke and have diabetes? A three-dimensional marginal could be, how many people smoke, have diabetes, and are male. Now, the higher order marginals will reveal more and more information about the person. So, for example, if I ask how many people have smoke, have diabetes, are male, are between 20 and 30 years old, live in San Francisco, and Hispanic, maybe there's only one person left in the database. So there's a trade-off between how many marginals we want to preserve in terms of accuracy, and we cannot preserve too many, because then we may violate privacy. So here we have a parameter that somehow allows us to tune between accuracy and privacy. And by the way, you can also express marginals in terms of the Fourier transform, because there's a natural Fourier transform that comes with the Boolean cube, the Walsh functions, the functions that we know from harmonic analysis quite well. The discrete Wall functions here would represent the Fourier transform, and the Fourier coefficients. For example, the second order Fourier coefficients, the second degree Fourier coefficients would encode the two-dimensional marginals. Like a Fourier transform, the second the second coefficients would correspond to your certain frequencies. So accuracy is encoded via marginals. Okay, then what is our goal? Our goal is we're given a data set on the Boolean cube. So these are the data x1 up to xn. Again, could be our patients, each with p parameters. And now we want to design an algorithm. It will be a randomized algorithm that creates first synthetic data on the Boolean cube. So the output should be a list of vectors y1 to ym. M doesn't have to be equal to n, so the data set can have a different size. That also lives in a Boolean cube. That's the first thing. We want to be able to create this data set efficiently. Computational efficiency is important. Then we want this data set to be private. Let's assume we want to use differential privacy here as notion of privacy. And we want this to be accurate, expressed in terms of accuracy of low-dimensional marginals. So these are the 4 properties we would like to satisfy on the Boolean cube. So this is our benchmark model. How hard can it be? Well, unfortunately, already this simple data model is NP hard to deal with. Ullmann and Vadan have shown in 2011 that you cannot achieve 1, 3, 4 synthetic data on a cube, privacy and accuracy, in a computationally efficient way. This is NP hard. In other words, you cannot have 1, 2, 3, and 4 simultaneously. It's impossible. So in a way, you're already done here with a simple no-go result. Because when you're faced with an NP hard problem, you can think now, what do we do next? We have to relax this NP hard problem a little bit. Well, the first thing you might come up with is, why is this NP hard? I don't really believe that this is NP hard. This is an easy problem. For example, why don't we simply add noise to the data, right? Simply add noise to the data, that gives you some privacy, and that should do it, right? Well, it turns out, yes, this is a very simple idea, but you have to add a lot of noise to really protect privacy here. This is really, when you do the calculations, you see the amount of noise you have to add is too high to actually then give you accuracy. So you cannot do that by simply adding noise to the data. It either the noise is not enough to give you privacy, or if it gives you privacy, the accuracy is gone. So we cannot do that. Okay, what else can we do in this case to deal with this NP hardness of the problem? Well, I will present you 2 things that we will do. First, we will relax the accuracy condition a little bit by using an on average accuracy definition. Instead of all marginals, most marginals shall be accurate. And second, we will circumvent the Ullmann-Vadan hardness result by realizing that this is a worst case result, but most data may not be worst case. Let's deal with typical data instead, and then we will see we can achieve in both of these situations, we can achieve 1, 2, 3, and 4. And this is the first time actually in both cases that this was achieved. Okay, so let me start with the first one. We go back to k-anonymity, and k-anonymity itself is such a simple idea, right? We want to create a database such that we want to modify it in a way that k individuals are not distinguished from each other. This must be easy, right? This cannot be hard. Well, if you want to do it in an optimal way, again, it is NP hard. So we are again in a situation where very simple things are really NP hard already. Finding the optimal partition into k-anonymous groups is NP hard. Optimal multivariate microaggregation is NP hard. I will explain in a moment what microaggregation is. But already in this simple case, we again face NP hard problems. Microaggregation. It's the standard way to implement k-anonymity, and you can think of it as clustering. So you give a data set, consisting of vectors xi. Again, this could be our patients. And the first thing is we cluster the vectors into clusters. Each of the clusters has size at least k. Okay, so we cluster the data set. Clusters, each cluster has size at least k. So this is different from k-means. unfortunately also k in the k-means, but k-means clusters into k clusters. Here we cluster it into clusters where the size is at least k. So this is different and harder. And then from each cluster, we pick a representative, yj, and this yj gives us k anonymity. So we replace the data set of x's by clusters. We pick from the clusters a representative yj, and these yj's make up our k anonymous data set. This process is very easy, right? This is really not NP hard. The NP hardness comes in when you try to do this in an accurate way. How do you measure utility? How do you ensure that you get something reasonably accurate with this procedure? And how do you actually, if you wanted to include privacy, how do you include privacy in this case? So these are two very difficult problems. And I should say, macro aggregation has been around for a long time, but if you look in the literature, there are no guarantees regarding utility, although only empirical results, but no utility guarantees. And well, we changed that. So the challenges of k-anonymity list here again, real-world data, high-dimensional and sparse. How do you do computation efficiently, high-dimensional space? How do you control utility? When you project in low dimensions, how do you make sure you don't lose all the information in low dimensions? And how do you actually control utility and privacy in low dimensions when after projection? So a lot of issues you need to handle. And we will handle them by actually solving a completely different problem. So don't forget, but put aside everything I said. And now we look at a completely different problem from theoretical probability. Something that it seems has nothing to do with privacy whatsoever, or nothing to do with microaggregation. I ask a very basic fundamental question in probability. How much information is lost when we take conditional expectation? It's a very basic question in probability. So let's look at it. I have a random variable x and a sigma algebra f. I define a conditional expectation. Y is the expectation, x conditioned on a sigma algebra. The law of total expectation says the expectation of x is equal to the expectation of y. This is a well-known result. The law of total variance is written down here. And the law of total variance implies that conditional expectation underestimates variance, right? The term on the left side is larger than the term on the left side is equal to the term on the right side. That means that the variance of x is larger than variance of y. So we underestimate variance by taking conditional expectation. We can ask how much variance is lost here. Well, let's do a simple example in one dimensions. This x is scalar. Let's assume x is a bounded random variable. We decompose the interval from -1 to 1 into k subintervals of length 2 over k each. We take the sigma algebra to be the preimage of these intervals, and then the conditional expectation can be bounded in this way here. That means the variance loss is bounded by 4 over k squared. So we can really bound the variance loss in this case easily. Can we generalize this to higher dimensions? Well, how does the law of total covariance now look like? Variance becomes covariance. Well, if we replace x, the scalar random variable x, by a vector, then the conditional expectation is still the same thing. It's y is the expectation of x conditioned on a sigma algebra. Now, instead of variance, we look at the covariance, and the law of total variance becomes the law of total covariance. And in particular, sigma x is larger than sigma y in the order of positive semi-definite matrices. So conditional expectation underestimates covariance. We lose some covariance, therefore covariance loss. And we can ask now, well, how much do we lose? How does this covariance loss depend on the sigma algebra complexity, and can we control this loss? This is a basic question in probability, but you find no answer whatsoever in the literature. So we set out to answer this question, and we cannot do what we have done before by simply dividing the space into intervals. then the curse of dimensionality would hit you, and this would not give you a good bound at all. K would have to be exponentially large in P to make this useful. Okay, nevertheless, you can solve this, and it turns out you do not suffer the loss of you do not suffer the curse of dimensionality. Indeed, you can bound the covariance loss nicely with this, what you get on the right-hand side, with this expression log k over log k. And C here is just a constant, independent of everything. So we can bound the covariance loss. This is the optimal, almost optimal result. This is optimal up to the numerator, this log k, which is a very small number. So this result is almost optimal. So we can bound the covariance loss. We can find an almost optimal answer to a question that comes from very basic probability. And almost magically, this extends to higher moments as well, which I've written down here. Something that's not obvious at all, because if you think of that, as we will later see, covariance is really a second two-dimensional marginals, then how can I bound covariance loss, higher order covariance loss, so three-dimensional marginals by two-dimensional marginals, something that's not obvious at all if you think of it from the Fourier transform point of view, because the two-dimensional, the Fourier coefficients, they correspond to frequencies of degree 2, have nothing to do with frequencies of degree 3, right? These are orthogonal. So this is not obvious why this bound holds here. But let's go back to microaggregation. What has this covariance loss to do with microaggregation? Well, let's start with microaggregation. We are given a data set x1, xn. We consider this data set from the viewpoint of covariance loss. That means we define a random variable xi, which has as nth trace this little xi. So this capital X is our random vector. And we apply the covariance loss theorem to this random vector. We get a partition. This partition is the sigma algebra, but this partition also gives us the way to do a proper microaggregation, because based on this partition that we get from covariance loss, we can do microaggregation. We can compute the representative from these clusters that we get in this way. And now we have performed microaggregation, but we also have performed microaggregation by we control the error that we make, because this covariance here corresponds to two-dimensional marginals. That means the microaggregation that we have performed comes with a control of the utility. And obviously what we do here gives us n over k anonymity by making sure that the cardinality of these sets that we do in this covariance loss theorem all have at least cardinality 1 over k. So we get n over k anonymity, and we get control on the utility. The whole thing, however, gets a little bit more complicated. And as I said, it extends to higher marginals as well. I will skip that for time reasons. But how can we upgrade this k anonymity result to differential privacy? Well, let me just tell you that this is not an obvious thing, and let me point you to a few challenges along the way. What's the issue here? So let's say these are the data points you're dealing with. You can think of these people living in Los Angeles, and here's an outlier. These people living in Houston, and here's someone living on the countryside. We want to do microaggregation for such a data set. Well, let's say k equals 4. This is one way to group this. The red dot is the representative of each of these groups. Now, for the left two sets, this is quite good. Here, the utility in the right set will maybe not so good, but that's what it is. Now, if I want to add privacy, differential privacy, then I have to repeat this whenever I remove a data point. I have to repeat the exercise and see what I get. So let's remove this point here. Microaggregation wouldn't change much, right? It just moves this point a little bit, the rest stays as is. So not a big deal. But what if I remove this point here? Then microaggregation would change a lot, right? Because now this one point changes the clustering a lot, and therefore also the representatives I get from these clusters. So differential privacy would be an issue in this case. Well, you could say, well, you chose a data set that is really tricky. Let's use a simple data set like this one here. Microaggregation is straightforward in this case, right? So these are three very nice clusters, no problem at all. Very low error. Now let's do differential privacy. That means I need to check what happens if I remove one data point. Let's remove this data point. Let's do microaggregation. We get the result very similar to before, right? And again, this is a very nice data set. Now, differential privacy again, let's remove this data point here. What happens is, well, all of a sudden, each point from a cluster, so this point here at the circle was originally this cluster. Now it moves over to this cluster. This point here was in this cluster. Now it moves to this cluster. So in each cluster, all of a sudden, one point moves to another cluster. And that means the whole synthetic data set changes because I simply changed one point. And don't forget, this is a very benign data set. So the point here is microaggregation is a very sensible thing, and microaggregation by itself does not play well with differential privacy. So this is really a very annoying thing. And therefore, the algorithm that we designed, which I will, for time reasons, not cover in detail, has to be very carefully constructed. We have to add noise in the right place. And the difficulty comes in because we do a spectral projection to reduce the computational complexity. We need to keep track of what's going on in the projected space. All this is done without any assumption on the data itself. So this is a parametric-free model. We have to control the cutoff in the eigenvector, in the eigenvalues, even though we assume no decay of the eigenvalues at all. And we have to add noise in the right way to balance privacy and utility. So a lot of steps here involved that make this very tricky. And you see here something that is called damped microaggregation. That means we have to deal very carefully with outliers, something that is a really big thing in the Census 2020 data. So this algorithm that I write down here, which I will not cover in detail, comes with a theorem that tells you it is indeed possible to do differentially private microaggregation where you get access to, we can really control utility and privacy in a way that you want. Now, the proof of this is a 30-page exercise with a lot of carefully calculated probabilities. I will definitely not go into that, but this is the first result of its type. Microaggregation has been around for 20 years, but for the first time, you can actually prove give a utility bound, and for the first time we also can tie it to provably accurate privacy bound. So this is the one result I wanted to tell you. The drawback of this algorithm is it comes with an accuracy guarantee that holds for most marginals, but not for all marginals. So that brings me to the second framework that I wanted to describe to you. Again, we have this best case result that two-dimensional marginals and Boolean cube and synthetic data all together is NP hard. This is a worst case result. It's for the worst kind of data. What if you look at typical data? What if you look at the statistical framework instead? So let's develop a statistical framework for data. That means we start with some probability space, omega, sigma nu, and the probability distribution nu gives the population model of the true data. And we assume that the true data X is a random draw from this model. But we assume that we do not know mu, otherwise we could easily generate new data. We cannot do that. And so we do not know nu. But we assume that we can sample from omega according to some probability that we measure that we choose. Again, our example is the Boolean cube. We do not know the population distribution in a Boolean cube. We do not know how the health records are distributed in a Boolean cube, but we can freely sample from the Boolean cube data that we want, right? According to some distribution that we choose. That's something we definitely can do. So how do we measure accuracy? We measure it before, as before with marginals, or more generally linear statistics. So linear statistics functions of this form, just think of them as good enough. And we want to, in this case, not the average error, but the maximum error. So this is a worst case error bound. And we want to make sure that the marginals are preserved up to some delta. Okay. The issue is, as before, omega, the Boolean cube, for example, is too large to do computations. but the number of linear statistics is much smaller. So we can do computations with respect to the linear statistics, but we cannot do computations on a Boolean cube. The Boolean cube, for example, is exponential in p. If you have p parameters, it's exponential in p, while linear statistics are typically polynomial in p. Number of two-dimensional marginals scales like p squared. The Boolean cube is 2 to the p. So one idea is, well, subsample the Boolean cube, replace it by some omega star. Choose a random subset of the Boolean cube, do your calculations there. And then we generate synthetic data on a subset of the Boolean cube, fit the statistics, and hopefully it's the right thing. But is this even possible? Can we subsample the Boolean cube and still get accurate results? Well, it's clear if the true population distribution and the sampling distribution are disjoint, if they don't talk to each other, this approach cannot work at all. So we need to assume some correlation between the true distribution that we do not know and the sampling distribution that we use. And we quantify this with the concept of the Rainey condition number that they define here. The Rainey condition number is in a nutshell simply the exponential of the Rainey divergence of order 2. It's like a little bit like the condition number in linear algebra. Its smallest value is 1, and it happens when these two distributions are identical. So if the Rainey condition number will be a mechanism to construct synthetic data with respect to this reduced space omega star, and do it in a faithful way. So the algorithm that I'm, for time reason, not really going through is, we start with the true data, you're giving me a family of linear statistics, and I create a reduced space by simply sampling, in this case, from the Boolean cube. It can be any other data model as well, but let's say the Boolean cube. And then I add noise to the linear statistics. I fit the linear statistics on this reduced space by trying to construct a density that matches these statistics. And then I do bootstrapping to create synthetic data. There's a theory that tells you can do all that. You can really do all that under certain conditions. You run this algorithm, you see what you get is privacy, you get differential privacy, and you get also accuracy. So we can prove that this algorithm, the statistical framework algorithm, gives you private synthetic data. And since what we solve is a linear program, we also can do it computationally efficiently. So there's a whole theory that tells you you can do this. You can do it in a Boolean cube, but there's no reason to stick with the Boolean cube. It works for very general data models as well. The last thing, so of course there are a few challenges, which I will skip for time reasons, but the last thing I wanted to mention to you is, whenever I mention differential privacy, I'm telling you we add noise. Everybody's doing that. There's no way to do differential privacy without adding noise in the literature, it seems. But adding noise has negative effects. It will affect your utility. And in particular, adding noise and introduces bias, and that's really a problem. And so the question is, can we get differential privacy without adding noise? Well, it turns out, yes, we can. We can do something that is called private sampling. We can modify the algorithm that I have presented to you before, this statistical framework. So we can get differential privacy without adding noise by replacing it with a certain carefully calibrated random sampling strategy. Now, the proof of this is, again, 30 pages, a lot of Boolean Foo analysis, hyperconductivity of Boolean functions, duality empirical processes. So this is a very technical thing, but at least I want to mention one little lemma here, the so-called private sampling lemma. That's simple to prove. I'm not proving it, but that's easy to understand. And this is really the key to doing differential privacy without adding noise. This private sampling lemma says you start with a set omega, you have a map that takes a data set X as input and returns a probability mass function f of X on omega. Now let's suppose that epsilon is larger than 0 and a k can be chosen such that if you evaluate f on this data set x1 and evaluate f on a data set x2, and the difference between x1 and x2 are, as in differential privacy, they differ only by 1 point. Okay, so you have two data sets, X1 and X2, taken from the original data set X, and they differ by only one element. You include a patient or not. And if you can bound this infinity norm by this expression, that should remind you of differential privacy, then if you can prove that, then you get differential privacy. And this is really the key, of course, to connect it to the statistical framework. You need a lot of extra work, but this really allows you to differential privacy without any noise. Why is this important? Well, this is ongoing work, so I cannot give you the results yet, but the US census data that will be released soon will be released with differential privacy added on. But that really causes a lot of problems, as initial simulations have shown. In particular, minorities like the tribal communities or other rural communities are not accurately represented. They're often underestimated by this noise. And that means they don't get enough money they should get, or enough resources. So the question is, can we use, instead of this Laplace mechanism, another way to create differential privacy, and in that way release more fair and yet private census data? So this is the one of the projects that we're working on, where we put all this theory to practical use. The other project is we're still working on synthetic data for the ICU case, where we try to construct multimodal synthetic data. Turns out to be very challenging. No surprise, because if you've seen already, the Boolean model is already so challenging. Here are the papers to all these what I presented. And as a conclusion, what I tried to present here is synthetic data are a really important thing in privacy, but it comes with tremendous mathematical challenges. Many of the problems, the simple problems are already in p-hard if you want to do them rigorously. So on the other hand, it's really a great area for mathematicians to get involved in, because it comes with great challenges, and yet, or not yet, and in addition, it's really useful and important for society. And there's a connection to another framework I developed a year ago, and you can look that up in a talk I gave a year ago. Here's a YouTube connection to this, where I advocate for a new paradigm in data science that allows us to take back control of our data. Thank you very much.
Well, thank you, Thomas, for this very informative talk. We are a few minutes past 2:40 already, but I think people who are here want to ask some questions. So I open the floor for some questions. I must ask the first one, maybe slightly technical, on your theorem of covariance loss.
Yeah.
So as I read it, you say there exists a partition. Is the proof of existence constructive? Do you construct the partition?
Yes, it is constructive. We construct the partition explicitly. That's important, because we want to use this later to really do microaggregation. So this is a very careful, delicate thing, but let me come back to this if I get the slide. It takes me longer to get to the slide and answer your question, sorry. But yes, so this theorem, yes, the sigma algebra that we construct is an explicitly constructed sigma algebra. And it's a very technical thing at the end. This is where we needed really much skills to dive deep into this. There's a lot of operator theory going on in the background, and that's really what we do here. Yeah, but it is explicitly, it's constructive, and it's feasible to do it. It's numerically efficient to do it.
Okay. Yes. And so the bound in K decays quite slowly. So, yeah, but that's still enough for your purposes.
So this is a good point. This is for the census data, for example. I think it is a problem because well, if K is large, it's not a problem. But you may have communities where really K cannot be that large, and then it is a problem. On the other hand, so this is a theoretical bound. It could very well be that in practice it is much better. For example, we did not assume any decay. What is happening here in the background is a spectral projection on the eigenvectors coming from the covariance matrix. We do not assume any decay of the eigenvalues here. If they decay fast, this bound gets much, much better. Mm-hmm. But we haven't assumed it here. It's completely, non-parametric. It could very well be that in practice this gets much, much better. We just don't know it yet.
And so in your situation, I mean, the result is valid for any random distribution. If you take a particular one, will there be improvement automatically?
Well, I'm sure I can find one that's really ugly and doesn't give you much improvement. For example, if the spectral projection doesn't give you any, if things do not, well, if I choose random data that are completely high dimensional, there's no low dimensionality going on whatsoever, then you won't be able to improve. But if you have high dimensional data that in truth live in some low dimensional manifold, lowish dimensional manifold, you should get improvements. But they can, the counterexample is choose something that's completely random and has no structure whatsoever, then this is the best you can do.
Okay. Do we have other questions? So let me ask maybe one of the quite vague questions about differential privacy. So that always requires a randomized algorithm to even make sense, right?
Yes, that's true. Yeah. Mm-hmm.
There's no other way to study that for a deterministic algorithm?
Well, no. You can come up with a different notion of privacy if you want, but differential privacy by definition has this built-in randomness in it. It's part of the concept already.
Are there
right? Yeah, go ahead.
Are there notions of privacy that do not involve randomness?
I mean, yeah, k-anonymity is a notion that doesn't involve randomness. There are generalizations of k-anonymity like T-anonymity and L-diversity. They're all kind of okay, but the problem is when I have a databases and I make, let's say, k-anonymity, but I link it to another databases, all of a sudden it's not anonymous anymore, right? The Netflix price, you may remember that, when in this database they released, you could actually identify the individual users by linking it to a different database. This is really problematic, right? I mean, we can do it, with location data. You can link it to a different database, and you can really track the movements of our president, for example. This is not a good protection. If your universe is closed and this database is all there is, then it's safe. But if you can link it to something else, which you can, then it's not safe. So this is the problem that all these anonymization techniques have. They're not really secure because there's a life outside this database. And differential privacy tries to mitigate it, but it's not the final answer, I think. There are other concepts of privacy you could envision. It's still an ongoing process, I think, to find a workable definition that does what we want, but it's also verifiable and not just, well, let's define it and we do something completely different in practice. Because what is this epsilon differential privacy? How does this really ensure anything? This is not an easy thing.
In the same line of ideas, I mean, here you talked about several data sets and then one. But if you have just one data set and you perform two encryptions on it, you had a slide, when you do anonymizations, you black the eyes, and you do the other one where you blur things. If you have those two, you can also reconstruct the original data set.
Absolutely. Yeah, you're absolutely right. It's a very delicate thing. Ideally, if you could do homomorphic encryption in a feasible way, right now it's computationally way too expensive. It's completely out of reach. That would be a great thing. It seems for the next 10, 20 years, this is, or maybe even 100 years, I don't know. That's not the way to go.
Other questions? Well, it looks like there are no other questions. So we'll thank you, Thomas, one more time. Happy with that.
Thank you very much.